Hi everyone! These animations are beautiful, aren't they? Well, but what are they all doing here? They all connected, but can you guess how? They are all connected either to Fourier series or Fourier transformations. These circles here are just circles of sines and cosines, which we've learned at school. These are representations of Fourier series, which we covered in our calculus course last year. And this one up in the right is the representations of discrete Fourier transform, which we'll speak about today. So our topic for today is discrete Fourier transform. Let's start from simple things. Remember what is vector decomposition? Any vector can be represented and decomposed into a set of appropriately weighted orthonormal basis vectors. And here we have vector r hat, and it is represented as a linear combinations, which is sum here, of vectors y hat and x hat, which are orthonormal basis vectors for r hat. But what about functions? Well, for example, for polynomials, we have Taylor series, which we also covered in calculus, but what if we have some periodic function? The questions are we able to decompose the above into a weighted sum of basis functions? If so, how to choose such basis functions? And how can we calculate the weights, so coefficients for basis functions? And the answer is Fourier series. Recall from our calculus course that a periodic function with period p can be represented as an infinite sum of weighted cosine and sine functions. This is called Fourier series. And this is a formula for Fourier representation of a periodic function. By the way, do you remember what are these a0, an, and bn here? If you don't, please just pause the video, take a break, and think of it. A little hint, it's connected to integrals. Let's move on. Actually, Fourier series is just a decomposition of a function into the orthonormal basis of sines and cosines. At first, let's take a look how it works. Any periodic function can be written as a linear combination of our set B, which is presented here. We compute the dot product between every function of the set B. So at first we compute it between cosines, after that we take the dot product between sines, and after that between sines and cosines. By doing this, we completed the dot product between every vector in set B, and in every case we get zeros here. So what does it mean? We have two facts. The first one is that it spans a t-periodic function's vector space, and the other fact is that each vector of B is orthogonal with each other vector in B, as we can see from these zeros here. What does it mean? Sure, it means that B is a basis for our vector space, for a vector space of t-periodic functions. What's next? So B is a basis, but our basis is not orthonormal. What can we do to make it orthonormal? Well, to make our basis orthonormal, we just find norms of every vector here and divide each vector by its norm. By doing so, we get B prime, which is an orthonormal basis for periodic functions vector space. What does it mean? It means that we can represent any t-periodic function as a combination of elements of this set B prime. In this video, we will talk about Fourier transform and discrete Fourier transform. And now, let's just take a brief overview of what Fourier transform is. From this animation, we can see that a function f is resolved into Fourier series, a linear combination of sines and cosines. The component frequencies of these sines and cosines are represented here on this blue line. And the frequency domain representation, f hat, is the collection of the peaks of frequencies. So this is a function over time, and this is a function in frequency domain.
Before going to discrete Fourier transform, let's talk about Fourier transform. And Fourier transform is something that decomposes a function of time into a function of frequencies. We just plug in this formula our f of x, so the function of time, and we will get our f hat of omega, the function of frequencies. It is very helpful in image compressing, in any data compressing, and any signal compressing. Because as well we can recover our function of time from the function of frequencies. It's also something like decomposing a function into the basis of cosines and sines. We call the Euler formula. So this is a very nice picture. It helps to understand this concept like pretty well. Here is our time domain. It's our function of time, and it goes to frequency domain, so the function of frequencies. It's something like decomposing. For example, in music, decomposing a chord on different notes, and doing by this formula. It's a very simple example because this function is 0 everywhere as there is the interval of from 0 to capital X. And let's calculate the function of frequencies f hat. F hat of formula is equal to just this integral. It's all about integrating. We plug in here a function. So in the interval from 0 to capital X, X is equal to A. And we just calculate this integral and get our Fourier representation. And for example, this is a Fourier spectrum on this function. DFT for discrete Fourier transformation. And actually, discrete Fourier transformation is just a discrete analogy of Fourier transform. We have a function and we sample data, so take some points on the function. And our discrete Fourier transform yields us coefficients near like specific frequencies. We'll discuss it in the next slide. We're just interested in extracting frequencies from data. Imagine you have this function. You can decompose this on like this basic function. So every coefficient fk hat is a coefficient near specific frequency. It's a formula for calculating these coefficients, this discrete analogy of Fourier transform. And this, like e to the power of minus 2 pi I k n divided by n, it just, from Euler formula, is decomposition of cosine and sine. And this number, 2 pi chi n divided by capital N, is just omega frequency. So meaning of f hat k is just near coefficient near specific frequencies, coefficients here. Discrete Fourier transform is just a linear transformation, so we can represent the sum like by a matrix vector multiplication. Our input is just our sample and output our coefficients near specific frequency, and complexity of this algorithm is n squared, so it's pretty complex. And simple DFT example, we have 4 points, so capital N equals to 4, and obviously delta x equals to 2. And let's just calculate of all f hats. We use this formula here. K is equal to 1, obviously. And by calculating this and like plugging in here Euler formula, we get minus 2i. It's the imagined part and the real part of this coefficient. And we can calculate all the f hats in the same way. So we get 10 here, minus 2 here, minus 2 plus 2i here. It's easy, guys. Have fun with LA.